Okay, so where did we leave off last time? I almost wrote with a pen on the iPad. Last time, what did we do last time? Right, we talked about curves. So Z from A, B to C was a smooth or piecewise smooth, maybe piecewise smooth curve. If it's if it's C1 or something, differentiable and the derivative is continuous, and two curves Z tilde from CD to C is equivalent to Z if Anna?
If there's a bijection between them.
Right. If there exists a map from CD, say, which is bijective. Anything else?
And we need the derivative to be greater than 0.
Yes, perfect. We need the derivative to be strictly positive, such that Z tilde of S is equal to Z of T of S. And once we had equivalence classes, then we could say gamma is a curve, not a parametric. Oh, I meant to put the word parametric. Parametric. In other words, I don't care about the parameterization. I want to think about the curve is curves up to equivalence. So this is a set of all curves that are equivalent to Z. That does form an equivalence class. And we saw that what we mean by, so this was a definition, what we mean by integrating f of z dz, which I will usually be too lazy and just write that, what we mean by is take some parameterization and that doesn't work because that's not dz, that's just dt. I'm missing
Z prime t.
Thank you. Okay. And then the definition is independent of the choice. And we proved, how far did we get? We proved that if f has a primitive, well, is continuous and has a primitive on omega, and gamma is a curve containing omega, and gamma starts at W0 and ends at W1. I'm sort of misusing notation. Then the integral of f over gamma, let's call the primitive capital F. Primitive means?
F prime is F. Big F prime is little f.
F is holomorphic and its derivative is little f. Yeah, antiderivative. Then how do you integrate over the curve? Just the fundamental theorem of calculus all together now. Okay, everybody's nodding. F of W1 some things are too stupid to answer, but I still hope we're all paying attention. Okay, and a corollary of that is under all of these same conditions and gamma closed, the closed integral is 0. All right. So we started talking about the relationship of this to Green's theorem. And in fact, that's kind of, I think, I have to check the history of this. I think that's roughly how, it kind of doesn't make sense to me. I really have to look this up. Because Green, I'm thinking 1850s, and Kashi, I'm thinking 1820s. So maybe this theorem was the precursor to Green's theorem. Let's remember Green's theorem. Just from real variables. We have a curve. How do I want to say this? I have some region, I have a region R whose closure is inside an open set I always like to have a little bit of room so that I'm never worried about what's happening at the boundary. And the region is, is its boundary. The boundary of the region is a curve gamma that encloses something. I mean, you have to say something about simply connected. Maybe really what I want to say is gamma encloses. Gamma is a simple curve, doesn't cross itself, and encloses a region R. In other words, it's exactly what you think it is. This is gamma. This is my region R. And if I have two functions, usually denoted P and Q, that go from R2 to R, and they're C1 in the sense of R2, so continuously differentiable. Then I can integrate over the curve, and now I need line elements. So if I do P dx and Q dy, those will be, so I'm measuring just how much you're moving, how much as you go around gamma, the dx changes, and I multiply that by P, and I measure as I move around gamma how much y changes, and I move around by Q. Okay, this is multivariable calculus. I think nobody needs me to take time on this. What do I get on the other side?
Partial Q by partial X minus partial P by partial Y. The area integral over the region.
Perfect. Okay. So this is Green's theorem. And let's use this to prove Cauchy's theorem, and then we'll see what the problem is. So Cauchy's theorem, as Cauchy originally proved it, I think, I have to look this up. Cauchy's theorem is that if F is holomorphic on some region omega. So remember, before, all we said was F is continuous and has a primitive. We didn't say F itself was holomorphic. F is just continuous so that I can define the integral. Then the integral over a closed curve is 0. And this is much more general. This is going to say F is holomorphic on omega, which contains a closed region, and the boundary of the region is omega. Then, or really, again, I want it the other way around, where gamma bounds. It's not, I don't want the boundary because R could be some region with holes, and then you have to worry about simply connectedness. This is part of the issue. If F is holomorphic on a region, then the integral over F, the closed. So having a primitive is one condition that tells you integrals over closed curves are 0. But being holomorphic also tells you that integrals over closed curves are 0 in the special case where we understand what region your curve bounds. Okay. Let's see how he proved this, and let's see what the issue was. What's the proof? Well, you apply Green's theorem, right? What is this integral? This integral over gamma f dz. Let's say f is equal to u plus iv. And what is z? Z is x plus iy. So what is dz? I mean, it's just dx plus I dy, right? As a differential. What does it mean to wiggle z? Well, you wiggle x and you wiggle y, and that's what it means to wiggle z. And so if I stick that in, I get an integral over gamma. F is u plus iv. Dz is dx plus I dy. Let's multiply this out. So what are the real parts? I get a u dx, and I get a minus v dy. Minus v dy. And then I get an imaginary component. I get a u dy and a v dx. just multiplying the pieces out. Integrals are linear. We can move things around. This is the imaginary part. This is the real part. Okay. Now let's apply Green's theorem. So what happens to this integral when you apply Green's theorem? So P is U and Q is negative V. So this becomes P and this becomes Q. So I get a double integral over the region that gamma encloses. And then what? Who shall I pick on? Hannah, are you volunteering? Is that? No? Okay. Thomas? Wasn't this your question, maybe?
Yeah. Yeah, sure. So you get what do you call it? You get negative v dx
Yep.
minus u dy minus du dy. Sorry, yeah, I'm left off the d in front of the dv, but you know what I mean. Yeah.
So we get an area integral, and the imaginary component, we get the same thing, but now this is P and this is Q. So I get Q sub X minus, I'm just following this formula, Q sub X minus P sub Y. Whoops, I meant to write Q is U. So I get U sub X minus V sub Y, dx dy. And then what?
You can use Cauchy-Riemann.
Beautiful, Anna. Cauchy-Riemann. Cauchy-Riemann says these two are negatives of each other, so they add up to nothing. And these two are equal, so they add up to nothing. Okay, so Cauchy-Riemann implies the whole thing is zero. All right, and this is how things stood for quite a while before people said, what do you really mean by this? By this kind of thing? This is the thing that people got very nervous about. Many people were arguing, what do you mean, what do I mean by this? It's obvious. I draw a picture, here's the interior. And it took people quite a while to be convinced that there was a need for the Jordan curve theorem. And then once Jordan proved it, there was quite a while before people were convinced that his proof was correct, and people gave new proofs and kept arguing about it. In fact, his original proof was formalized in theorem provers. So yes, it's perfectly fine. It follows all the axioms, but there was a long argument. So to avoid making this precise, making this argument precise via Jordan curve theorem, and taking care of that, we will do what the book does. We bypass it. We bypass these difficulties with a beautiful argument of Goursat, of course proved much later, with a beautiful, well, it's up to you to decide if it's beautiful. I think it's beautiful. Argument of Goursat.
Can you elaborate on what exactly is the difficulty? Like,
well, what does this mean? I give you a curve. It's closed. How do I figure out what its interior is?
okay. So isn't the same problem applicable to the Green's theorem then?
Yes. And when you learned Green's theorem in calculus, you just ignored it. You just drew a picture and said, I know what gamma means and I know what it bounds.
Okay.
Yeah. I don't know how your multivariable calculus teacher stated this, but for the most part, people just bypass the fact that there's any question there. Because no one's thinking about curves that are fractal and you know, some Koch snowflake type thing and
yeah.
Right? where's the interior? You zoom in on one of those, you cannot tell the inside from the outside, right? It can be as ugly as you want, and somehow you're still supposed to be able to tell what you're integrating over and what orientation and whatnot. So in actual multivariable calculus, that never happens. So you say, of course, I know what it means to boundary region, but this was also the time where people were getting serious about rigor, because things were breaking. They weren't just getting serious about rigor for the sake of rigor because they were anal or something. No, the mathematics was breaking. People were proving contradictory things. Kashi himself proved that limits, I think I said this last time, limits of continuous functions are continuous. And Fourier said, here are Fourier series that converge to any function you want. It doesn't have to be continuous. So one of them's wrong. I mean, in a sense, both were wrong, but until those ideas were made precise. All right. So what's the argument of Goursat? Goursat says, I don't know about general curves. There's no question about what the interior of a triangle is. So I'm just going to prove Cauchy's theorem for triangles. So Goursat is Cauchy for triangles. For triangles. And you might think this is pretty stupid. Like, how are we going to get anywhere just from triangles? The curves are much more general than that. Just you wait. There's so much mileage he's going to get out of this. All right, so theorem of, well, it's Cauchy's theorem, but done elegantly. Let F be a map from some region to C, which contains a triangle, the closure of a triangle. So whatever my omega looks like, I don't know. Maybe this is my omega. It can be as bad as you want, but it contains the interior of a triangle. So let's see. How shall I denote the interior of the triangle as opposed to its boundary? Well, I'll just write T for the triangle. So a closed triangle is contained. My regions are always open, so there's always a little bit of room around it. And of course, the boundary of this is, I'll just write boundary of the triangle. Okay. Then, and F is holomorphic. So F holomorphic implies the integral over the boundary of the triangle of F of Z dZ, if we want to be pedantic, is 0. This is, of course, a closed integral because a triangle is a closed shape. How does he go about proving this? It's a brilliant bit of, I don't know. It's very simple. Here's the idea. The idea is, well, it uses a couple of ideas, actually. It's rather elegant. So here's what you do. You take your triangle. Let's move this down. I'm realizing when I give you the PDFs, you see the line. See here, I don't see the line. It just looks like an infinite blackboard. Keeps going down and down and down. Proof. So here's what I want to see. I want to see a big triangle. Here's T, whatever it is. Doesn't have to be equilateral or nice or something. I'm going to say that T is T0. And what I'm going to do is subdivide, just take all the midpoints, and you get these 4 similar triangles. And I'll call them T11, T12, T13, and T14. So I get 4 similar triangles. The side lengths are half as long. The diameter, the largest distance you can reach, is half as long. The perimeter is half as long. Okay, so and my claim. So of course, T, when I say integrate over T, I have to give you an orientation. The curves with opposite orientation are not the same. The integral will come out to the negative of the other integral. So the orientation I'll give a triangle is the usual one. Okay. As theta goes from 0 to 2 pi somehow. A right-hand orientation. We're a righty, majority rules. Okay, so the orientation of T0 is like this. And the very simple claim is that the integral over T0 of F is the same thing as the integral over T11 plus the integral over T12 plus, I guess I'm only skipping one thing. I'm that lazy. that the integral over the 4 triangles is the same as the integral over the original triangle. Why is that true?
I mean, just because integration is linear and the sets are disjoint except maybe for their boundaries?
Well, let's see. I'm integrating over the boundaries. They're different. They're genuinely different curves.
Sorry.
Yeah.
You're integrating over the boundaries, not the regions.
Oh,
yeah.
sorry.
So they
but
cancel. They have opposite orientations along the boundaries. So
exactly.
those cancel out. Yeah.
I forgot I was calling. I forgot if I was calling T the triangle or the boundary. Yeah, exactly. The boundaries are canceling out. All of the interior boundaries are being traversed forwards and backwards. And so the contributions, the various interior contributions cancel. So interior contributions cancel. Okay. So what? Well, all right. Then we can certainly say that the integral over the original triangle is no more than the sum of all of these. And let's take the biggest one. So let J1 be the max of, well, the argmax of these things. In other words, either the first triangle or the second or the third or the fourth is the largest. It has the largest contribution in absolute value. So so this integral is dominated by 4 times whoever was the worst one. Boundary T1, J1. I don't know which one's the worst, but who's ever the worst, it's
what is
worth
the
4 times.
argmax?
Yes?
What is the argmax?
Oh, argmax. It's if I just said max, it would give me the largest integral. Argmax means give me the value of J, which contributes the largest integral.
Okay.
Does that make sense? Is that something you guys are used to? I mean, I don't. I could just write it in words instead of being. This is the J, such that absolute value of T1J, such that, let's try that again, the integral over the boundary of T1J of F in absolute value is largest. Is that better? So whoever is the worst guy, of course, the sum of all 4 of them isn't larger than 4 times the largest one. All right, so here's what we're going to do. Let's say T4, let's say 4 was the largest guy. Okay, so let's say 4 is equal to J1. Now I zoom in. Now I zoom in on T1. So zoom in on T1, 4. Or J1. And of course, we're going to proceed by induction. Proceed by induction. So when I have the integral, it's a closed integral of the boundary of Tn Jn, whoever was the largest guy of that integral of f, that will be an absolute value bounded by 4 times the integral of T n plus 1, J n plus 1, whoever the worst guy is as you go in farther. Okay? So we're thinking of like, sorry, you can't see. So we're thinking of like T1 is here, and then T2 is here, and then T3 is here, and then T4 is there, and T5 is there, and so on. So we have this nested family T0 which contains T1, which contains T2, and so on. And, well, I want to know what's going on. What's going on? So my claim is that, notice that all of these are closed triangles, and they're bounded, closed and bounded, so they're compact. These are each compact. So if I have, this is a general fact, if I have some sequence, some decreasing sequence of compact sets, and non-empty, of course, non-empty, then there exists a unique point Z such that the intersection, and of course the diameters are shrinking, and the diameters of the TNs are going to 0. The triangles are getting smaller and smaller. Then there's a unique point Z so that the intersection of all of these is the singleton Z. Okay? Proof? Well, how do we get, let Wn be the midpoint of Tn. So every triangle has a point that's, half, whatever, you know what I mean. You know what the midpoint of a triangle is. It's half the distance in each direction. It doesn't matter, we should take any point. I'm just giving you a point. Take any point in each of the triangles and look at the sequence Wn. Wn is a sequence inside T0, and T0 is compact. What do you know about a compact sequence?
Has a limit?
Has maybe a subsequence has a limit. So there exists Z, which is the limit maybe of a subsequence of these Nj. Okay, and this Z is in T n for all. I want to say that this Z is in Tn for all n sufficiently large. Yeah, this is for all n, in fact. This is in Tn for all n. Why? Well, they're nested. Right? So Z is in T0 and it's in T. It's also a limit point of T1 and Tn and so on. Okay, so which implies Z is contained in the intersection over all of them. Why is it the only limit point? If there exists a W in the intersection of the Tn's. So if you could zoom in somehow and get 2 points in the limit, then the distance from Z to W is less than the diameter. They're both in each Tn. But the diameters are going to 0. And there's no n on this side. So the only number that's less than epsilon for every epsilon is 0. So that implies W is equal to Z. Okay, so it's unique. So so existence is just using compactness. Uniqueness is using the fact that the diameters are going to 0. All right, just some baby topology. Maybe you didn't. Maybe you're already convinced, but we want to do this properly. So the triangles. You have these triangles, and you're zooming in, and there's a unique limit point that all of the triangles are zooming onto. Now, Z. So we've proved this claim. Okay, so far so good. Now this Z is in all the triangles. In particular, it's in omega, and F is holomorphic in a neighborhood of z. So near z, i.e. for n sufficiently large, because if I want a ball, well, once the diameter of the triangles is small enough, then I'm in a ball. For n sufficiently large so that the triangle Tn is sufficiently small. Near z, that is for all w in at Tn for n sufficiently large, f of w is equal to f of z plus f prime of z, which exists, times w minus z plus little o of w minus z. That's exactly what it means for the derivative to exist. Once you've zoomed way in, f is linearized. This is a linear function in w. So far, so good? Does that make sense? So we've zoomed way in. We started with this initial triangle. We did all this stuff to zoom into some other little triangle over here. In this neighborhood, linearize f. Linearize f. That's all we've done so far. Now let's look at the integral over the boundary of Tn of f of, I guess I should call this w dw, since z is my fixed point. Should I call it z0? No, it's okay. Z is, let's not change notation. Z is this point that we've zoomed in on. So near zero, near z. Okay? This we can express as, so we're going to plug in all of this for f. So we're integrating over the boundary of Tn of f of z dw. Z is fixed. W is the dummy variable. Plus f prime of z, w minus z dw, plus some function that goes to 0 faster than w minus z goes to 0 dw. What do you know about this integral? Z is a constant, w is the dummy variable. Can you think of a primitive? Constant times w is the primitive, right? So this has obvious primitive. And so does this. Because it's just a polynomial in z. It's a linear polynomial in z. And we're integrating over a closed curve. Now we can use our previous theorem. If we have a primitive, then that part's gone. Has a primitive, which implies the integral over a closed curve of those pieces is 0. So all that's left is this. So this is equal to an integral over the boundary, Tn, of some function that goes to 0 faster than w goes to z. Now to this we can apply, so now let's take absolute values. To this we can apply, we had a lemma that a function, if you integrate a function over a curve, that's bounded by the supremum, just take the worst value of the function over the curve, times the length of the curve. So this is less than the supremum times the length of the boundary. Now, what is the supremum? Well, what's the value of this function? It's something that goes to 0 faster than w minus z goes to 0. So it's something going to 0, little o of 1. How far is w from z? Rishab?
The diameter.
Diameter, perfect. It's the diameter of Tn. So it's something that goes to 0 faster than the diameter of Tn. And what is the length of Tn? Well, it's the length times the length. of the boundary of Tn. Does that make sense? Okay, now wait a second. Where did we get all of this? So far, so good. Is everybody happy? So far, so good. Where did we get all of this? We started with this statement. And of course, if we iterate this statement, we pick up a factor of 4 every time, 4 to the n. Oh, sorry, that was a 0. Well, let me redo it here. The integral over the original triangle of f is bounded by 4 times whoever the worst T1 was. Of course, I mean boundary. And if we iterate that, every time we take a new triangle, we lose a power of 4, a multiple of 4. I mean, we lose in the sense that it's getting bigger and bigger. We're trying to show the integral is 0. Times this integral over the smaller enough boundary, and we take n small enough so that we can localize, we can linearize f. We take n large enough that the triangle is small enough. We've zoomed in near this limit point z, so we can linearize f. And what we've shown is that this has an upper bound. So this integral, we just bounded by that. So we have this massively growing factor of 4 to the n. And this integral is bounded by something going to 0 as n goes to infinity, times the diameter of Tn. What is the diameter of Tn? What's happening to the diameter every time we zoom in one triangle more? Shrinking by a factor of?
I guess shrinking by a factor of 4 to the n, probably, or something to the n.
It's something to the n. If you just look at the triangle, look at this triangle, we bisected the sides. So we get the same triangle, just the sides are half as large. So the diameter is also half as large each time. So we're only gaining here in the diameter, we're only gaining a factor of 2 to the, a half to the n, times the diameter of the original, triangle. That's not good. Not good enough. Wait a second, what's happening to the length? The perimeter of the triangle. Every time it shrinks by a factor of, altogether,
2 to the negative n.
Yeah, every iteration, it picks up a factor of a half also, times the length of the original triangle. And now we're golden. The factor of 4 that we lost is offset by these two factors of 2 to the n, and because f is holomorphic, we still have something that's going to 0 as n goes to infinity. So the whole thing goes to 0, and we have something bounded by something going to 0, which implies the whole integral was originally 0 to begin with. Questions? Does this make sense? Okay. Let's take a little break. Okay. So we just proved that if f is holomorphic and this contains a triangle, then the integral over the boundary of the triangle of f is 0. Corollary, if f is holomorphic and this contains a rectangle, then the boundary of the rectangle, if you integrate over f, is also 0. Why? I have a rectangle. Yes, it's two triangles. Okay, rectangle, which is the boundary of a triangle plus the boundary of another triangle, and the interiors go in opposite directions. All right. Now we get a really cool theorem. If F is holomorphic on an open disk, yeah, just open an open disk, then F has a primitive. So here's a disk somewhere. This is D. Then F has a primitive. Being holomorphic on a disk means you have an antiderivative. This should be somewhat surprising. I mean, how are you going to define it? In fact, when you think about it for a second, it's clear how you're going to define it, but then you have to check that what you define will make sense. Okay, let Z0 be the center of D. Doesn't have to be the center, it could be any point, but I'll just choose the center. For every Z in the disk, I define a curve, gamma Z, which is move horizontally, then vertically. So if I have some point Z, wherever it is, here's Z, I move horizontally until I get to the right real part, and then I move vertically until I get to the right imaginary part. And this will be gamma sub Z. So starting at Z0, from Z0. Okay, so far so good. Now I define capital F of Z as the integral over this curve of F with some dummy variables. And I claim that's the primitive. Of course, it should be the primitive. It's the integral of F. Shouldn't the derivative of the integral of F be F? That's what we have to show. Okay, it's a well-defined function because it doesn't matter how you parameterize that you're moving along this rectangular-looking thing. All right. So claim, of course, is that F of Z plus H minus F of Z over H goes to little f at Z for all Z in the disk. That's what it means to be differentiable. That's what it means to be holomorphic. Let's see how we can prove it. So let's look at 1 over h f of z plus h minus f of z. Let's make h small so that z plus h is also in the disk, of course. So again, here's my picture. Here's the disk. Here's z0. Here's z somewhere. And here's z plus h somewhere. They're both in the disk. F of z plus h is an integral. So there's a 1 over h in front. There's an integral over gamma z plus h. Gamma z plus h is this. This is gamma z plus h. But this is gamma z. So I have an integral over gamma z plus h of f minus an integral over gamma z of f. So check this out. So integrating over gamma z is the same thing as integrating over the reverse instead of coming this way and that way. So I can, so you can think about going from z to z0. In other words, this is equal to plus the integral over gamma z with the opposite orientation. So instead of going from z0 over and up, now I'm going to go down and over. That's gamma z minus coming to z. And of course, with z plus h, I'm going like this. This is z plus h. So over these bits, this bit and this bit cancel out. Okay. Then I'm moving over this bit, this bit. I'm going to add and subtract this direction and that direction. Okay, so let's keep track of some of this. Well, let me just write it in words. So let's call this the tails. They're the tails. Tails cancel. Then you make a rectangle. Okay, so we have a nicely oriented rectangle here. What's the integral of f over the rectangle? 0. So integral over the rectangle of f is 0, as we just proved. And so all that's left is an integral that goes from z across and up to z plus h. But even there, we can add a curve that goes straight line down and straight line up. And now we have an integral over a triangle. What's the integral over a triangle? 0. So what we've shown, make a triangle, and the integral over a triangle, and boundary of the rectangle, boundary of the triangle is 0. So 1 over h f of z plus h minus f of z is equal to 1 over h times an integral over the curve that goes straight, the straight line from z to z plus h. Let's call that gamma. Just call it gamma. Can I just call it gamma? It doesn't need a name. Maybe gamma z to z plus h or something. I don't know. Gamma z to z plus h, f. F of w dw. Okay? And it turns out at this point, so really the theorem will say any function which is continuous in the disk and has the property that the integral over any triangle is 0, has a primitive. There's a stronger version of the theorem, which we don't need. But all we will use at this point, all we use now, is that f is continuous. So we used holomorphicity to apply Goursat's theorem to say integrals over triangles are 0. But if all we assume is continuity and that integrals over triangles are 0, then we get this. Okay? By continuity, what does continuity mean? Continuity, so continuity implies f of w. You see, now we've zoomed way in. Now h is very small, so we're in a tiny neighborhood of z. All the action is happening in a tiny neighborhood of z. So f of w is f of z plus, well, something that goes to 0 as w goes to, let's say, big O of, well, let's just say little o. How do I want to say this? Little o, let's just say big O. Big O of w minus z. Just something that goes to 0 as w minus z goes to 0. Not faster than w minus z. Continuity means the value of f of w approaches the value of f of z. So as w goes to z, the difference between the two things goes to 0. That's all I'm saying. Okay. I guess I'm saying a little bit more because it goes to 0 linearly. How do I want to say this? Well, we know much more than this because we know it's not just continuous, but it's holomorphic. So this is indeed true, but never mind. It doesn't matter the rate. This rate doesn't matter. Oops. This rate doesn't really matter. Though for holomorphic functions, it's true. All right. So let's go back over here. This is equal to 1 over h times this integral of f of z dw plus an integral of something smaller. Let's just call it little o of 1. That's what I should have done from the beginning. Instead of telling you the rate, it's just little o as w goes to z of 1. It's just something that goes to 0 as w goes to z. That's all I want. Okay? Little o as w goes to z of 1 dw. Okay? F of z is a constant. I know a primitive.
Should that integral, I mean, it says f of z dw. Is that still?
Yes, f of z is a constant.
Oh, okay.
We were integrating dw, so I'm replacing f of w here by this stuff. And I'm still integrating with respect to w. So this is a constant. So it pulls through the integral. And what's the primitive of 1? A primitive of w. Yeah, w, okay? Everybody knows? So what does this integral come out to? F of z is a constant. And then we have the function w evaluated at z plus h. So this is times w evaluated at z plus h to z. Because those are the two endpoints. And the derivative of w is 1. How about here? What can we bound this by? We can bound it by the length of the function, the length of gamma, times, well, something that's going to 0. As h goes to 0. So now this is, as h goes to 0, certainly w goes to z. And now hopefully you see the end. We get a 1 over h. There's a constant f of z. Of course, this will be z plus h minus z, also known as h. And then this is big O. What's the length? The length is h. And little o of 1. And so when I divide by h, I get f of w. F of z. I'm just taking this constant f of z. So I just get f of z plus h over h. I just get left with little o of 1. So that's it. We have a primitive. So this is f prime of z. Any questions?
So this also would have worked if we just took like the straight lines from z naught to z and to z plus h, right? And created that little triangle, right? Was there a particular reason we went over and then up?
Just to make rectangles, you could very well, you can do this in all kinds of ways. Let me do an aside here. So you're suggesting that we just take the straight line. And if I have z plus h, then I have that straight line. And by the same token, we could have just gone straight across and made a triangle and killed it off. In fact, I like that better. Why did Stein do rectangles? He wanted to use the rectangle theorem. He proved the rectangle theorem. But we proved the triangle theorem. Here's the triangle theorem in action. Yeah, no, I like this better instead of going over and up. The going over and up is to prepare for toy contours, which we're about to do if I shut up and get moving. But I don't want to rush. Questions? Other questions? Does this make sense? Anna, it's good. Rishab, Hannah, Birchin, make sense? Great.
I guess I'm also just a little unfamiliar with the difference in big O notation and little O notation.
Oh, I'm sorry. I thought we spent a little time working on it, but I think I didn't. So let's say you have two quantities, x and y. X is big O of y if and only if there exists a constant such that x is less than the constant times y. In other words, big O is bounded by a constant, and x is little o of y if x over y goes to 0. So what I'm saying here is this integral is bounded by a constant. In fact, the constant is 1. 1 times the length times the sup norm of the integrand. I'm using that theorem again. So this is the length of gamma, which is h exactly. And the sup norm of the integrand, whatever it is, it's going to 0 as h goes to 0. And it's bounded. I just want to say that, yeah, this error term is bounded by something like this. In fact, the constant is 1 in this case, but I'm getting you used to big O and little o notation. It takes a little while to, and not only does it take a little while to get used to it, it takes a little while after you're used to it to get it right. So I encourage you to try to play with it and see if you can get accustomed to it. Once you start using it, then it's very, you don't write epsilon 1 and epsilon 2 1,000 times. Okay. So did that confuse people, the little o notation? Stein doesn't use it, and so if you want to read Stein's version of this in the book, he'll use epsilons and such. I want to give you an alternate viewpoint. Okay. Great. Great. All right. Let's do something. So here's a theorem. Let's call this exercise or example. Example 1. We're going to start using toy contours to prove all kinds of things that, in principle, we have no business knowing how to prove. Okay. Fourier transform of the Gaussian. Fourier transform of the Gaussian. What in the world do I mean by that? The Gaussian, f of x, there's a variety of ways of normalizing it. I'll take that to be the Gaussian. And by Fourier transform, I mean f hat of xi, which is the integral over the reals, e to the minus pi x squared. So let me give you the general formula. For any f, it would have been f of x e to the minus 2 pi I x c dx. So that's a Fourier transform. I want to compute this integral. So this is an integral that you could have been given in, I don't know, grade school, maybe. If someone was mean and didn't give you all the tools that you needed to solve something. I'm integrating over the real line, e to the minus pi x squared times e to the minus 2 pi I x c. Now, first of all, does this converge? What's the absolute value of e to the minus 2 pi I x c? 1. It's e to the 2 pi, e to the I times a real number. That's on the unit circle. Okay, so in absolute value, it's like e to the minus pi x squared. Awesome, you know, supermassive convergence out in infinity in both directions. No problem with convergence. Absolutely convergent. Okay, what about xi equals 0? In other words, f hat of 0 is the integral e to the minus pi x squared dx. That maybe you should have been given in multivariable calculus. Does anybody know what the answer is? Oh, Hannah, I thought you were holding it up. You were very close to holding it up because you had one finger in the air as you were thinking. The answer is, I claim the answer is 1. How many of you have seen this before? Some version of it? Let's see why. Okay, so let's call this integral I. So what is I squared? I squared, I'll just open up and use 2 dummy variables. E to the minus pi x squared, e to the minus pi y squared, dx dy. What does pi have to do with the Gaussian? If I didn't put the pi there, it'd be e to the minus x squared. What in the world does pi have to, the circumference of a circle? Are you mad? Yeah, exactly. Rishabh's doing it with his, yeah. We're going to convert to polar coordinates. So in polar coordinates, dx dy turns into dr d theta. What's the Jacobian? I'm writing x as r e to the I theta and y as r e to the, I'm writing z as r e to the I theta, r cosine theta, and y is r sine theta. The Jacobian is you guys don't memorize r dr d theta? That's like yeah, you've seen that before, right?
Okay. Oh, I thought you wanted the full Jacobian.
Well, the determinant of
right. I forgot the 2 meanings.
Yeah. So r ranges from 0 to infinity, right? I'm just doing polar coordinates. R, this length is r, this angle is theta. Theta goes from 0 to 2 pi. And I have e to the minus pi. This is e to the minus pi x squared plus y squared. But x squared plus y squared is r squared, right? E to the minus pi r squared. Now, aren't we going in circles? How did this help us at all? We have the same integral, e to the minus pi r squared. Have we gained anything? Rishabh?
Like we can switch the integrals, or like we got a rdr term.
Yes, the r, the Jacobian is saving us. Now this thing has a nice antiderivative. Right? What's the derivative? What's ddr of e to the minus pi r squared? Well, it's e to the minus pi r squared, but then there's this stuff that comes down, minus 2 pi r. But we've got the r. We picked up the r from the Jacobian. And so if I want exactly e to the minus, if I don't want this constant, then I divide both sides by minus 2 pi. And there's our antiderivative. Of course, in theta, it's just a constant. This is equal to 2 pi in theta. And then e to the minus pi r squared over minus 2 pi, evaluated from 0 to infinity. At infinity, we get e to the minus infinity, so that's 0. And at 0, so this is 2 pi times 0 minus, at 0, I get 1 over negative 2 pi. Okay, also known as 1. I squared is 1, so I is plus or minus 1, but but I is obviously positive. Okay, so that's what the Gaussian has to do with the circle. It's that the Gaussian is a distribution that when you take 2 copies of it in the plane, you see the bell, you see, right? The Gaussian by itself, e to the minus pi x squared, you just see this bell. You don't see a circle. But in 2 dimensions, that bell is a circular bell. How do I draw this? I should use Mathematica or something, right? It's radial. That's where you get the circle. This is the wrong picture. You need to take that bell and spin it. When you spin it, then you see pi. Okay, 3 minutes left. Let's go. So we know. Okay, any questions on this? So far, so good. So we know that f hat of 0 is equal to 1. Great. How about f hat of xi? Let's say xi is positive. F hat of xi, again, we're trying to integrate over the real line, e to the minus pi x squared, e to the 2 pi I guess I said minus 2 pi I, depends on how you want to normalize things, dx. How in the world are we going to get our hands on this integral? So here's my claim. Look at, let's see, I'm using f for something else. Well, actually, no, let's look at the same f. Look at f of z equal to e to the minus pi z squared as a holomorphic function. Okay, so this is entire, in fact. Entire, it's holomorphic on omega equal to c. There's no problem defining z squared. There's no problem defining the exponential function. And take the contour, take the rectangle, minus r to r. This is xi. This is r plus I xi. And whoops, negative r plus I xi. Take this rectangle. Let's call the rectangle gamma. And oriented in the usual way. Right-hand rule. What is the integral over gamma of f dz? For any r, fix r. Of course, we will send r to infinity in the end. Xi is fixed. Xi is whatever value of f hat of xi we're trying to determine. Zero. Zero. This is a rectangle. Rectangle. This is holomorphic. Okay? All we've done so far is we have a holomorphic function. It's on a disk, but that disk can be as big as you want. Disk of radius 2r, whatever. R is bigger than xi. We have this rectangle. Great. But it's also equal to the sum over the components. So let's call this gamma 1. This is gamma 2. This is gamma 3. And this is gamma 4, right? It's piecewise rectilinear. So it's a sum. This is equal to integral over gamma 1 plus gamma 2 plus gamma 3 plus gamma 4. Now what's happening to the integral over gamma 1 of f? 0 from minus r to r, right? F of z dz. So we have to parameterize it. What's the parameterization? Z is equal to how about x? We're on the real line. X ranges from minus r to r. That's a and b. Z prime is equal to 1. And so this is the integral from minus r to r, e to the minus pi x squared, because z is x. Z prime is 1, dx. And what does that converge to as r goes to infinity? That's what we just computed. Good thing we knew the answer. So far, so good? I'm out of time, so I'm going a little fast. Maybe we'll start with this next time. You're going to get a lot of practice with contour integrals. Don't worry. Hannah, am I going too fast? It's okay. Thomas, good? Okay. How about over gamma 3? The integral over gamma 3, over the top part of the rectangle. How are we going to parameterize that? Z is equal to x plus I xi, as x goes from r, well, you can't write this, but I'll write it anyway. It goes from r, maybe I'll say it's the negative of the integral over gamma 3 minus, and in gamma 3 minus, I'll go from negative r to r. Is that better? Somehow it doesn't feel right to say x goes from r to negative r. So I'll flip the orientation. Instead of going backwards, I'll go forwards, and that negates the integral. Okay. So what is this? It's negative the integral from minus r to r. Right. Now we have to be a little careful. E to the minus pi z squared. This is x plus I xi squared. What is dz? Z prime with respect to x is the parameterizing variable. It's still 1. Yep, z prime is still 1. Z prime of x is still 1. C is a constant. Dx. Who's with me? Hannah, are you having trouble reading, or should I zoom in a little? Something you don't like. Hannah? Take me back.
A second.
I'm rushing, so it's better not to rush and have everybody following along. But I'm out of
Wait,
time.
why? Okay. Why is why are we writing z equals x plus I? Is that C?
C. Yeah, that's a C. Sorry. C. Oh, that's not much better. C. So I'm looking at this part of the curve.
Oh,
Gamma 3.
okay. Okay.
So it's at height IC, that's fixed, but X is what's changing from R to minus R. And that feels really weird to write, so I'll take the negative of the curve in the opposite orientation. So X will go from minus R to R, but I just have to put a minus sign on the curve. Is that good? Okay. Let's multiply this out. What do I get here? I get e to the minus pi x squared plus 2xix minus c squared. So what do I get in total? Since there's a minus sign, the xi is a constant. The xi is a constant. So I have an e to the minus pi negative xi squared. That's an e to the plus pi xi squared. That's a constant that pulls all the way out. Integral from minus r to r, e to the minus pi x squared, e to the minus 2 pi x c I dx. And what happens to this as r goes to infinity? That's exactly what we're trying to compute. F hat of c. As the r goes off to infinity. For any fixed c, c is fixed. Okay, we're almost there. I'm going over. I was going to say 5 minutes. We're already 5 over. Can I finish the calculation, or should I let you go? Finish the calculation. We're almost there. All right, let's do integral over gamma 2. I'll do it quickly, and then maybe I'll do it again. Gamma 2 is like this. So on gamma 2, z is equal to r is fixed plus iy as y goes from 0 to c. Right? I'm just going straight up the line. I'll write it again here. So on here, z is equal to r plus iy, where y ranges from 0 to c. So I get e to the minus pi z squared. Z prime, what is z prime now? 1. I, right? This is the y is the parameter. So I get times y times dy. Okay, but this we'll be able to bound rather easily. Sorry, and now okay, so this is equal to the integral as y goes from 0 to c. The integral over gamma 2 has a range, and it's as y goes from 0 to c of this stuff. And now let's bound this. I'll bring the absolute values inside. Okay, we have to open this up. So here we get an r squared plus 2irc, exactly as we got before, minus c squared. So I get a e to the pi c squared, that's a constant, and then an e to the minus pi r squared, and then something of absolute value 1, and then I, which also has absolute value 1, dy. I'm confusing you. This is a y. I'm confusing you because I'm writing things that aren't correct. This is a y, so I get a y and a y. And this is a pi y squared. That's better. All right, I'm going to finish it in 1 minute, and then we're going to review it next time because I'm really taking too long. Integral from 0 to c. I'm going to upper bound this by replacing y by its largest value, which is c. So this is less than or equal to e to the pi c squared, e to the minus pi r squared dy. Well, that's equal to, now the integral in dy is just the length, e to the pi c squared, e to the minus pi r squared. C is fixed. R is going to infinity. This goes to eggshell. And so in total, and the same thing for R4, so same with the integral over gamma 4, being not 0 itself, but going to 0 as R goes to infinity. So as R goes to infinity, let's put all the pieces together. One piece was, so we had the total integral over gamma, which is 0. It's equal to the integral over gamma 1 plus the integral over gamma 3 plus two things that are going to 0. Gamma 1 was 1. Gamma 3 was all the way right here. Gamma 3 was minus e to the pi c squared times the thing that we're trying to compute. And that's equal to 0. So the thing that we're trying to compute, the Fourier transform of the Gaussian, is, when I put it to the other side and divide, the Fourier transform of the Gaussian is the Gaussian. Okay, sorry I went over. We reconvene on Tuesday, and we'll continue from there.